Hi, my name is Dan DeBlasio, and I'm a PhD student in the Department of Computer Science here at the University of Arizona. This video contains an expanded explanation of how the advising process works, and in particular, how we utilize the Protein Multiple Alignment Accuracy Estimator, Facet, to find better alignments. If you've not done so already, I encourage you to watch our short introductory video for background on why we want to do this. Let's first review what the problem is. Most alignment programs, or aligners, come preloaded with a default set of parameters. These are things such as the cost to insert gaps, or dashes, and how much a penalty it is to align one amino acid, or letter, with a different one. These parameters are normally very good for almost all sets of inputs. In fact, a lot of research has been done in the field, including in our lab, to find parameters that do the best in general. The problem is, no matter how good parameters are in general, there's always some sequences that cannot be aligned well using them. This is why we developed the idea of parameter advising, and additionally, aligner advising. Parameter advising process, as pictured, generates several candidate alignments using different parameter sets. Then, using our estimator, Facet, or feature-based accuracy estimator, we choose the one that looks the best under our criteria. So let's take a look at how Facet works. We start with features. These are easily calculable measures of things that we know to be true about good alignments. So given an alignment such as this one, what features make it good? One thing that's useful in answering this question is secondary structure. Proteins fold to make structures that perform functions in a cell. Conservation of this folding is very important to preserving function. This secondary structure allows us to label each amino acid in an alignment as either alpha helix, shown in blue, beta strand, shown in yellow, or coil, shown in gray or white. We can then measure things not only on the sequences themselves and the gaps, but also on this secondary structure. Once the alignment is labeled, the first thing you might notice is that these labels seem to be in contiguous blocks of the same type. Using this idea, we develop a novel measure called blockiness, where we try and find a covering of blocks on top of the alignment. We can then find a set of these blocks that maximizes the number of amino acid pairs that are covered. This feature, in fact all features, are positively correlated with accuracy. This plot shows true accuracy versus the blockiness score for a set of example alignments for which we know the true accuracy. Each of the 12 features that we use are correlated with accuracy, but none of them work well as an advisor on their own. So we combine their values together to get a single measure of quality. As an advisor, we want the estimator to rank alignments. So we want to set the coefficients such that this rank is preserved. Let's look, for instance, at these three alignments for the same set of sequences. We would like our estimator to preserve the rank in true accuracy using only the value of estimated accuracy. If we look at any pair of them, we know the difference in true accuracy and the difference in estimated accuracy. We can then define the error on any pair of alignments as the difference in these two values. If we set the coefficients to minimize this error over all pairs of alignments, when we get a new set of sequences that we do not have the true accuracy for, we will also be able to rank the candidates correctly. Once we are able to rank the alignments correctly, we also need a good set of candidates to choose from. If all the alignments to choose from are poor quality, then no matter how accurate our estimator is, the chosen alignment will be poor. The problem can be solved optimally given an estimator. Here's an example of how it works. Assume that we have 3 alignments for each of 3 sets of inputs. The inputs are labeled by color, green, blue, and red, and the 3 parameters or aligners are labeled by letters A, B, and C. What we would like is that for any cardinality of parameters, choose the ensemble that has the best average alignment accuracy when we choose the alignment with the highest estimated score for each input sequence. If we want only the one set of parameters, this is equivalent to picking the best default parameter. In this case, we want to choose parameter A. While for red and blue, it's not the best, any other single choice performs poorly for one of the 3 inputs. But if we wanted to choose two aligners for advising, we would choose B and C. Together, with our estimator, they choose the three alignments highlighted, which have a better average accuracy than just those chosen with A. For the green input, we no longer have the option to choose the alignment with the highest absolute accuracy. But this loss is less than those gained from the red and blue. So once we have an estimator and the alignments, we can use this for parameter advising, and it does well. Using 10 parameters, we can improve the alignments that are hard to align by up to 27% accuracy. This chart shows the set of example alignments divided into bins based on the accuracy of the example under a single default alignment. The ones in the lower bins are harder in the general case. Using Facet as an advisor, the average alignment accuracy for the chosen alignments is shown as the red bar for each bin, and several other alignment estimators are shown in other colors. The solid line shows the performance of an estimator that chooses an alignment at random, the set of candidates. The oracle is an advisor that always returns the true accuracy, and provides an upper bound for how any estimator can perform. The Facet software, parameter sets, and our papers are available at the Facet website, facet.cs.arizona.edu, and you can contact me if you would like to have more information or have any questions. If you are using or plan to use Facet, we would love to hear from you.